Let me show you how to be a good Bayesian.
My guest today is Matthijs, Hollanders, a postdoc at the University of Newcastle in Australia. Yes, there is a Newcastle in Australia, where he spends his days analyzing camera traps and song meter datasets and building Bayesian models that take that messy ecological data seriously. The reason I wanted Matthijs on the show is his R package, occARU. It does something I find conceptually clean and refreshingly honest. Instead of collapsing camera trap data down to did we see the species today, yes or no, it models the counts directly. That choice unlocks a whole family of richer questions about detection rates, multi-species co-occurrence, and how all that varies in space and time, and the package handles it all with, you guessed it, hierarchical Gaussian processes, global, local, shrinkage priors, and some of the newest stand features around zero-sum and simplex constraints. So, as you know now, all of these are a bunch of show favorites. So, if you have ever wondered how Bayesian thinking actually helps ecologists get more out of their data, this is the episode for you. This is Learning Bayesian Statistics, episode 159, recorded May 13, 2026.
Let me show you how to be a good Bayesian. Change your predictions after taking information in. And if you're thinking I'll be less than amazing, let's adjust those expectations. What's a Bayesian? It's someone who cares about evidence.
Welcome to Learning Bayesian Statistics, a podcast about Bayesian inference, the methods, the projects, and the people who make it possible. I'm your host, Alex Andorra. You can follow me on Twitter at Alex_Andorra, like the country. For any info about the show, learnbayesstats.com is the place to be. Show notes, becoming a corporate sponsor, unlocking Bayesian merch, supporting the show on Patreon, everything is in there. That's learnbayesstats.com. If you're interested in one-on-one mentorship, online courses, or statistical consulting, feel free to reach out and book a call at topmate.io/Alex_Andorra. See you around, folks, and best Bayesian wishes to you all. Matthijs, Hollanders, welcome to Learning Bayesian Statistics.
Thank you.
Yeah, how was my Dutch pronunciation?
It was perfect. You nailed it.
Well, we'll see if at some point I learn Dutch. I think I will not unless I have to go live there at some point, to be honest.
It's hard to justify learning another language, especially if you have no reason to speak it on a regular basis.
Yeah, exactly. Especially since Dutch people actually speak such a good English, So all the Dutch people I've met in my life speak perfect English. So I'm like, well, no incentives.
It's pretty well the last country you'd actually need to learn the language to be able to communicate with the people there. So,
yeah. I have a friend who lives there right now. He's German, so actually it's very close. Like German and Dutch are super close, but he still hasn't learned Dutch because everybody speaks English.
Well, to be fair, I don't speak a word of German. I don't reckon the two languages are all that close together, but maybe it just shows to my skills of learning languages.
I mean, you live in Australia, so Yes, you're not living in Germany, so the comparison here is not it's not a perfectly controlled trial. But actually, we were talking about that just before recording. So you're the first person I meet, and I'm the first person you meet whose last name is also the name of a country, because your name means from Holland, basically, from what you told me, right?
That's right. Yeah, I think it's fairly unusual.
Okay, well, I think it fits well because we've got the World Cup going on. And so perfect. Today game is Andorra and Netherlands. So that's perfect.
That is perfect.
And actually, let's dig into your background, because you do interesting stuff. So maybe tell us what you're doing nowadays and how you ended up working on wildlife data analysis.
Right. So I'm currently doing a postdoc at the University of Newcastle in Australia, where I'm looking at analyzing basically camera trap data sets. Before that, I was working on song meter data sets, which it's microphones hanging up in the bush that record information continuously, basically. And there's a lot of overlap between those two data types. So that's what I've been focusing on the last couple of years, I'd say. Before that, I was doing my PhD, and I was doing mark recapture analysis, which is basically just another type of hidden Markov model that I'm doing right now. So I think a lot of the modeling that I've done has kind of been very similar, but answering different questions.
Okay, yeah. So I already see some similarities with other episodes we've recorded. The one with Aaron McNeil obviously comes into mind, where actually also worked on that model with him. He's leading a fantastic team, and they are doing modeling to infer the trade of shark meat around the world, and so they are using a bunch of very, very cool Bayesian methods to do that. It's an extremely complex model, one of the most complex I've ever worked on. But that has been super fun to work with them on that, and that was episode 127. I'll put that in the related episodes for this one, and also the one with Vianney Leos Paraja. She is doing a lot of hidden Markov models. So this one will hit close to home for you, Matt, and so people who wanna hear more about these kind of models, I will put that in the show notes. And that was episode 14 with Vianney. So this is one of the oldest ones. Damn. So lots of hidden Markov models, things like that. So fun fact for listeners, because I saw in your email signature that you were at the University of Newcastle, and as an ignorant person who just relies on their priors, I thought it was Newcastle, England. And so that was interesting when you told me you were in Australia. I was like, oh wait, there's a Newcastle in Australia.
I had to beg you to change the time, otherwise I would have been here in the middle of the night.
Yeah. The original time was 1 a.m. for you, so but actually it's better now that I'm in California. It's actually much easier to record with Australians than it is to record with people in Europe. So I thank you for that, because otherwise now I have to wake up very early to record the episodes. So that's good. And actually, how did you end up in Australia? Is that related to the kind of models and data and animals you have access to, or that was just kind of random?
It was definitely related to the animals mostly. I've been interested in wildlife my entire life, and I'm actually from the Netherlands, but I spent some time in the US, which really opened my eyes to what it's like to live in a place with lots of wildlife. And I always knew I didn't want to stay in the Netherlands, and I'd shortlisted Australia as a place I'd like to live. And during my master's, I just looked for PhD opportunities in Australia just to get me over here, because I just wanted to live here to live here. The specific choice of PhD was a bit of an afterthought. But yeah, that's how I ended up here. And yeah, so my work didn't really bring me here, but during my PhD, I became very interested in the work I'm doing now.
Yeah. Okay. So it's like really you really fell in love with Australia in a way.
That's right. Yeah. And it was, I think, to be quite honest, it wasn't the best to do my PhD for those reasons. I don't think I did a PhD for the right reasons, and I found it quite stressful at the time. But here we are. I landed on my feet, so can't complain.
Yeah. It sounds like it. And yeah, I still have to visit Australia. I visited New Zealand a couple years ago, actually with Aaron, because we were working on the model over there, and that was absolutely incredible. And I've been meaning to come back since then, and also come through Australia at that time. So yeah, definitely want to do that at some point.
Well, maybe before you come to Australia, I can convince you to come to the Yucatan Peninsula in Mexico for the International Statistical Ecology Conference in January 2027.
Oh yeah, you definitely can. That sounds very fun, and actually much closer to home. So for sure, let me send that my way, and I'll see how I can make that happen. That'd be fun to record some episodes over there. Actually, that would be
It's a
that'd be great.
fantastic conference. It's every 2 years. 4
Mhm.
years ago, I think it was in South Africa, so I could really justify going. The time
Damn.
after that, it was in Wales, so I couldn't really. But now that it's in Mexico again, where we have neotropical rattlesnakes and lots of
Mhm.
margaritas, I think
Mhm.
it'll be easy to go.
Yeah. Yeah. That sounds perfect. Yeah. Yeah. Send the links my way for sure,
I
please.
will.
And what about Bayes, actually? Because you do a lot of Bayesian models, but what drew you to Bayesian stats specifically?
Well, that's also easy to answer. It kind of starts with being at uni. During my master's and bachelor's, I think I took 3 or 4 classical statistics classes, and I never understood what was going on. I always found it incredibly not intuitive, and therefore, when I started doing my PhD, and I knew I was going to have to analyze these kind of complex mark recapture data sets, I needed to have a proper analysis. So I was like, okay, I need to actually sit down and learn this stuff. And it was the Introduction to Bayesian Statistics in Wind Bugs by Mark Carey, one of the like introductory JAGS bugs books for doing analysis. And it's when I feel like I need to do something, I can either rush myself and get frustrated, or I sit down and just go as slow as I need to go until I get it. And that's what I did with this book. I went chapter by chapter, like hand copied all the code. It never ran, always took it 20 times to rewrite it, even though it was only like 10 lines of code, because I literally had no idea what I was doing. But as I went, I became very interested in it. And yeah, that was definitely the beginning where it all started, probably 6 years ago now. And since then, it's completely changed the way I think about everything, because I've always written stuff in JAGs or bugs. Like, you have to write the generative model out, which I'm sure I don't need to tell you how good that is for forming an intuition around what you're
Mhm.
doing, or
Mhm.
getting an actual mechanistic understanding of what a model is doing. So that's definitely where it started. I have to credit Mark Carey really for all of those books that they wrote for ecological modeling.
Hmm. Wow. Yeah. Yeah. That makes sense. And yeah, these models are very complicated. So starting with those, this is that's hardcore. Well done, because
It's
this is clearly not the easiest.
they are both complicated and not complicated, in the sense that they're only complicated, or not only, but one of the main reasons they're complicated is because the data is messy, because we're not perfectly observing animals, because we're not surveying at set times all the time. So we have all this like almost like infrastructure around the model that is complicated, that you need to account for. But it's also not complicated in the way that a lot of these complicated models can be thought of as just some flavor of GLM still, which I'm sure we'll get into it in a bit. But yeah, I'd say most of the complexity comes just from how messy the data is that you need to accommodate. But under the hood, you're kind of still doing classical things like GLMs and linear models on different model components.
Yeah. Yeah. Um, and they're super fun also to work on, to be honest. And that's also because they are not that easy. That you always have something to learn. There's always a complexity or nuance you didn't know about, and so there is always something you can add on top of it, and that really makes a difference. And actually, let's set the stage for the listeners who don't work in ecology. Again, I recommend listening to Aaron's and Vianney's episodes, because we go into the details of capture-recapture models, especially with Vianney. But you focus a lot, and at least today we'll focus a lot on occupancy models. So, yeah, set the stage for the listeners about what that is and what problem that's actually solving.
So, occupancy models are used to accommodate for the fact that we don't always detect a species when we go and survey for it. So a lot of animals are rare, so you might only see it once every few times that you go and visit a site. So instead of just modeling the naive detections, like let's say we have 100 sites and we go and visit them once and we find the species at 50% of sites, we would never think that the species only occurs at 50% of sites. We only detected them at 50% of sites. So what occupancy models do is they add this repeated measures component where you survey every site multiple times, and that lets you estimate a detection probability, where, for instance, a common, highly detectable species, you see it almost every time you go and survey at a given site. So if you're never getting it at a site, it's probably not there. Whereas if there's a rare species where the sites where you did get it, you only get it 1 out of every 3 visits, every 5 visits, every 10 visits. So that's a rare or hard to detect species. And therefore, some of the sites where you never detected the species, they might be there. You just didn't pick them up, because basically what it's telling you is that if the species is there, you're still unlikely to see it.
Yeah, that's a very good, I think that's a very good way of explaining it, and that makes it very intuitive, because, like, everybody can understand that some species, some animals are harder than others to spot. And so basically this kind of model.
A different way that I like to think about it now is that an occupancy model has a zero inflation component, which happens at the level of the site. So the feature of occupancy models is that every site is surveyed multiple times. And what we're estimating, the first part of this model is this site occupied, yes or no, which is a latent variable, because we know it's occupied when we found it, but we don't know it's not occupied when we didn't find the species. So we're estimating this zero inflation parameter at the level of the sites, but conditioned on that occupancy state, we have this detection history, which lets us estimate the detection probabilities or detection rates at those sites. And that's kind of what I meant before about ecological models are complicated, but they're also not. If you can sort of wrap your head around that, the zero inflation is not happening at the level of the observation as it does in a typical zero inflated model, but it happens at the level of the site, then you're kind of back at just this, model that's in our toolkit.
Yeah. And added to that, you also work on automated recording units. So which is ARU, and so what's that? I actually don't know anything about that. What is special about that kind of data, and why do traditional occupancy models struggle with it, if they do?
So automated recording units are things like camera traps and microphones that are hanging up in the forest, basically to detect birds or vocalizing mammals. And it's in the name. They're just these devices that are essentially monitoring continuously over a deployment period. So a camera battery or an SD card might last like 2 weeks, but during those 2 weeks, it's running the whole time. But there's ways to extend it as well. Like you could have battery packs, or you could only have the camera be on for 1 hour every day, could be on every other day. So the key feature of it is that it's this thing that's actually monitoring continuously in time versus the traditional types of surveys that we would do where a human would go and visit a site for half an hour, 6 hours, 2 days, and look for the species, and then record in our notebook if we detected the species or how many we detected. The key feature is that the surveys are not discrete, really. They're occurring in continuous time, which is different from how the traditional survey methods work. And I wouldn't say that occupancy models struggle with the kind of data. It's just that the models were kind of designed for discrete surveys as opposed to stuff that's going on in continuous time, like these kind of devices.
Mm-hmm. Okay, yeah, thanks. That's very clear, and that actually illuminates some of the modeling choices we're gonna talk about next, because you created an R package to just that kind of models that you called occARU. So occupancy and ARU, and actually isn't occARU something special in your field? Is that even an animal?
I don't think so. The way I
Okay.
thought of pronouncing it was occARU, but maybe this is a good signal that the name isn't chosen that well.
Yeah, I mean, I like occARU. It sounds like an animal, you know. Look at that occARU. Yeah. Like
Yeah,
you could
you're
say
welcome. You're welcome to call it. You're welcome to call it that.
that. So actually, the most important part is, what is it about? You know, why did you create that package? And what's the elevator pitch for it?
Well, elevator pitch might be hard because I feel like I always end up talking a long time when someone asks me this question, but I'll try and keep it brief. There's kind of two motivations here. The first one is that in a traditional occupancy model, we normally record whether or not we detected the species, yes or no, during the survey. So we collapse our data to a detection or non-detection event, aka a 1 or a 0. And a lot of analyses that are done even with ARUs, so camera traps, people will end up, for instance, binning their survey periods to 1 day or 1 week of camera trapping, and then collapse any detections of the target species to a 1 or a 0, as opposed to modeling the counts directly. And my view is that this kind of happened because, well, when occupancy models were proposed, what they call the observation model, so the detection side of things, was a Bernoulli or logistic regression, where you modeled the detection or non-detection during a given survey. In my view, this collapses the actual raw data, which is a count, to a 1 and a 0, or a 1 or a 0, before doing any modeling at all. And you are throwing away information by definition when you collapse a count to a 1 or a 0. And my main motivation here was to be like, we shouldn't do that. Or if you're going to do it, you need a justification as opposed to doing it by default. So there are issues, of course, like autocorrelation between detections. Like you might have a group of 20 kangaroos that's standing in front of a camera for 2 hours, which will really ramp up your detections. So I put some features into the package which lets you thin detections. So for instance, you could have a 30-minute thinning window where it retains the image with the highest count during that window. So going back to the kangaroos, let's say they are there for 2 hours, that would be reduced to 4 detections with the maximum number of kangaroos in an image during each 30-minute window. So it might be like the group in the camera might range from like 7 to 17 individuals. So it would retain the highest count because that's the highest that we know was there at any given time during that window. But regardless of the thinning, the idea is to just not just go to 1s and 0s, but model how many did we see, because all else being equal, if you're seeing more kangaroos in 1 month than the next, there were probably more kangaroos in the system in that time. And I'm treading carefully here because this is a highly contested issue in ecological modeling, where the holy grail of ecological modeling is estimating abundance, for which the gold standard is mark recapture analysis, where you have actually tagged individuals, recapture them over time, and you're essentially modeling these time series of individuals surviving in the wild. But the key part of those models is that we have individual identification, which means we can track them over time. There are methods that exist where you use the counts directly to estimate an abundance, but those models are quite sensitive to model assumptions that are very hard to meet in practice. And one of them is, for instance, that you need to have independent counts of independent individuals. If you're double counting individuals, that throws out the abundance estimates. And that gets very hard to do with animals that are hard to individually identify, like kangaroos, or, plug in any mammal that doesn't have clear patterns like stripes or spots or whatever. And it gets very hard to do. But nevertheless, I still don't think that justifies collapsing counts to just ones and zeros, because how you choose to interpret the information that's in those counts is up to you. But you might as well model them before just collapsing it to a 1 and a 0 before you even start your analysis.
Yeah. And so actually that was one of my following up questions, was about that choice that you made in occARU, which is to model the counts directly rather than treating the detection as a nuisance parameter, which is exactly what you just talked about. I can see why that's definitely a meaningful shift conceptually, and how that'd be very useful. And basically, instead of throwing away that information, you do want to have it as much as possible in the model. And then if you actually want to throw it away afterwards, well, maybe, but you don't have to. And
exactly, you can just fit the count model and then be like, I'm not interested in interpreting this at all. And that's another thing, actually, where in occupancy models, usually the focus is on the occupancy of any given site, which is just to say, does this species occur here at this site? Yes or no. That's all occupancy is. It's just a 1 or a 0 for if the model thinks that the species was there. Another argument that I'm putting forth is that when you have these continuous deployments of camera traps, simply focusing on this binary presence-absence of species is almost kind of boring. Like, we have much richer data, right? Like, we potentially have these cameras running for months at a time, potentially repeated over many seasons. And to just basically have your target of inference be if the species, or at which site the species occurs, that still comes out of the package, because that's just what occupancy is. But I think it's much more interesting to focus on variation in the detection rates over time, especially when you get longer deployments. Like, I've had some data sets that are many years, and you get to see these crazy fluctuations in underlying detection rates of all your species. And it just gives you a lot of insight about what's in your data that's beyond just occupancy. So what I'm saying is, this package still gives you occupancy like any traditional package might do, but it just also lets you focus on those detection rates. So you don't lose anything, you only gain stuff. And it all comes from the fact of just basically not throwing away information in your data before you even begin modeling.
Yes, completely agree. And you have also some very cool stuff in there where you have the options for hierarchical, spatial, and temporal Gaussian processes to help for multi-species modeling. Obviously, I was very charmed by that option, because I'm a fan of GPs. So, can you unpack that for us? Can you tell us what that's doing, and what scientific questions it lets ecologists ask that they could not before?
Yeah, sure. I'll start with just the justification for having these spatial and survey effects in there to begin with. And just from first principles, when we essentially have repeated measures at two levels, at the level of the site, because every site is surveyed over potentially many days, many weeks, many months. And also at the survey, because usually we have a grid of cameras. So every survey period, let's say every day or every week that these camera traps are active, we're actually getting measurements from multiple camera traps. So we have repeated measures at the level of the site and survey. And there's plenty of literature that talks about what or how you should handle that. But the key thing is that you essentially have pseudo replication in your data if you don't account for that somehow. So the way I account for that is a random site effect and a random survey effect. And then it's just a question of how do we actually model these random effects. So typically you might have a normal distribution where all of these random effects are coming from, where you're estimating some standard deviation. That's just your run-of-the-mill random effect as implemented in any R package. With our site and survey effects, those sites and surveys aren't necessarily independent, because you would think that sites that are closer together are going to be more similar, and you would also expect surveys that are close together in time would also be more similar to each other. And once you get into this spatial and temporal sort of correlation structure, you're basically knocking on the door of a Gaussian process where you're constructing a covariance matrix over all the sites and over all the surveys. So the way I try and explain this as an elevator pitch is it's just a random effect that looks at these spatial and temporal locations of where we're collecting our data. Where the multi-species comes in is the package is designed to not just look at data from one species, but to look at data from all the species that are recorded. And the motivation here is when you look at your raw data of a camera trap or a song meter, essentially what you have is a timestamp and a species label of what we found. And that means if we have multiple species, we probably should have a random effect for every species and every site, because not every site's going to be good for each species. And then you get into the multi-species Gaussian process thing, where you still have the same Gaussian process kernel, but now you have a realization from this for each species. And there's actually a way to do this to make it quite computationally efficient, that you only have to do one Cholesky decomposition, even though you're getting these draws for all of these species. And it ends up being matrix normal, which I hadn't come across matrix normal until about 2 years ago, but it's basically a matrix of values where you have a row and a column covariance. So if you have a row covariance that governs the correlation between your sites, you have a column covariance that governs the correlation between your species. So what you get is not just these spatially structured random site effects and random survey effects, but you can also directly estimate how species are correlated in these effects. So for instance, you can estimate whether two species are likely to co-occur in space and time based on this multi-species process. Now I imagine that's quite a lot, but that's what it gets you that I don't think I've seen implemented in other packages. And if I had to say how the package like clearly differed from other things that are available, it would probably be how the multi-species hierarchical nature of the model is handled.
Mm-hmm. Yeah, and that definitely makes sense. I think it's a great setup for a GP. So that makes sense that you have that in there, and also then the hierarchical nature of your data also marries really well. So that's super fun to see that in there. How did you end up implementing that? Like, are you using vanilla GPs or using approximations? How are you handling the speed and efficiency side of the GP sampling?
Yeah, there's a couple of ways. At the moment, the GPs are still exact, and that's simply because so far most of the data sets that I've come across haven't been crazy in the number of sites that they have. So often you'll have like 100 or a few hundred, which I feel still works well for an exact GP. Also, I have built in a feature where often we'll have different grids of cameras in different locations, so essentially independent grids. And when I have independent grids, it does a separate, smaller GP for each region, which just assumes that the regions are independent. They still share the same hyperparameters, but you don't need to construct a full covariance matrix. You do it by region. So if you have 1,000 cameras in your data set, that would be an expensive GP to compute. But if those 1,000 cameras are split between 10 different grids, then you've got 10 smaller ones, which is actually way easier to manage. And it is definitely something I want to add is some form of approximation. And someone recently told me about GP tools, which is I think it's some sort of package that's implemented in Stan that lets you, I want to say it's Fourier transform GPs, but some sort of approximation for the inevitable case that you do have a huge data set where you actually need a massive covariance matrix.
Yeah. I don't know GP tools per se, but maybe they're using HSGP under the hood most of the time. If you're in a maximum 3D case for a GP, that's gonna be extremely helpful. And so for spatial temporal data, should work because that's 3D. And that's same flavor as a Fourier transform, and that really is a game changer for big data set because it just becomes almost linear in compute time with your data size. So that's amazing.
I do have code laying around because I've implemented them in the past for the HSGP stuff. So it's honestly probably something that will be in the package in the next month or so.
Yeah. I mean, that's really helpful. I mean, if most of your data set are not too big, that's awesome. It means you can use exact GPs. This is rare, but this is great to hear that is possible.
It's not that rare in camera trapping because just most of the time people are bottlenecked by resources. And I think it would be not uncommon to have a data set of thousands of cameras. I do think it would be unusual for all of them to be part of the same grid as opposed to split into multiple smaller grids where you can actually just do them separately within each region. But even there, the approximations would end up being faster, I'm sure. So worth implementing regardless.
I mean, depends on the approximation because you have some approximations that actually work less well than a vanilla GP if the dataset's not big enough. So, kind of like a central limit theorem kind of stuff where if you're not in the regime where the approximation accuracy kicks in, then you actually want the vanilla GP. So
I've actually
if you can use the vanilla GP, just do that. It's like you have the mathematical guarantee, and that's great. In my case, that's been super rare. Like most of the time, I cannot use vanilla GPs, and I've had to use approximations, and thankfully there are some now. And also the compute we can use is just so much better now. But it's good to have the different options, I guess.
I have wondered about that with a spatial GP where you have two inputs, basically a latitude and a longitude. And the way I understood the HSGPs, you have a basis function for each dimension or a number of basis functions for each dimension. So if you set it to the default of like 20, it ends up being 20 times 20, I think, because you need the combinatorics. So you end up having to estimate a lot of coefficients, which when you have a smaller field, I could see how that would be not ideal.
Yes, exactly. Actually, the choice of hyperparameters for HSGPs is extremely important, and is going to impact a lot the accuracy of the model and of the predictions. So this is it's always trade-offs, right? But basically, the approximation is valid for a given universe, if you will, and the hyperparameters partially determine that universe. And so you definitely want to pay a lot of attention into how these hyperparameters are chosen. In PyMC, we have that function that Bill Engels and I developed a few, I think, last year or a year and a half ago, something like that, where you pass a bunch of constraints that you want on your covariance, and then PyMC will do some optimization under the hood to find the optimized hyperparameters for you for the model. It's basically the same thing as what you would do by hand, but just automated, and it's a bit more user-friendly. A bit like the find constraint prior function that I worked on, that I merged like now a few years ago in PyMC, where you could just tell PyMC, hey, I'm looking for a gamma function with 95% of the mass between this and that. What are the good parameters to do that? Now it's in Prelise, and it's so much better, and Osvaldo Martin and colleagues made that a awesome package that's so much better than what I coded at the time. But that's kind of the same idea. Yeah.
That's good. I should probably look at that, because I wanted to add some functionality to automatically determine the length scales based on the input
Right.
of the GPs, because you can set the priors. Well, you can kind of set the priors. In the model, I've basically decided on the prior distribution for each parameter, but you can set the hyperparameters yourself. And so it has some sensible defaults, but it would be nice to input, for instance, the distance matrix for your sites and then determine a suitable length scale based on the input.
Yeah, especially since, I mean, in your case, it's a specialized package. So that's actually very good, because most of the people are going to use the package for the same kind of models. The difficulty we have in PyMC is that it's a generic package. So tons of people use it for very different use cases. And so we cannot make a lot of very informed default like that. So the function we have to find the hyperparameters of the HSGP, you need to provide a length scale. You need to provide a covariance function, the length scale, and like a couple other parameters that I'm forgetting. But you could go one level of abstraction, because most of your users are going to use it for occupancy ARU models, and so you can have very, very good informed defaults on that already on the length scales. So exactly. I think you can just go on the PyMC source code, find that function. I think it's called find HSGP hyperparameters or something like that. And like start from here and add a level of abstraction on that. That'd be very good from a user-friendly perspective.
Yeah.
But that's super exciting. I think it's awesome that you're making access to GP like that much easier, because as I always say on the show, GPs are amazing. They are in itself, even though they are a beautiful mathematical object, they are in itself an approximation. Like no real process in nature is really a GP. You're using a GP because you don't know the actual mathematical process underlying the phenomenon. Otherwise, you would just use the mathematical formula for it. But they are super powerful because they are so flexible. And I mean, there are neural networks, right? And we all know how good neural networks are. And so GPs are just infinitely neural networks with an infinite number of hidden layers. And that's what neural networks converge to. And they are just amazing because of that. But they are a bit complicated to understand from a theoretical standpoint. I mean, there is a high barrier to entry. And then also the barrier to entry tends to be high for practitioners, because you don't have a lot of packages that make access to it very easy, and also make them available in packages that people are already using for other kind of models. So often there are specialized packages just for GPs, maybe for one kind of GP, you know, which is like, if you don't know the research, you're like, what even is that GP? You know, so yeah, I think making GPs more accessible, especially when it makes a ton of sense here, that can really be a game changer for practitioners.
Yeah, initially I didn't even have the option that you could turn them off because the package started off a bit more opinionated, basically about the fact that we need to accommodate for these repeated measures through random effects. And
Right.
as complicated as GPs are, the way I explain them to people just getting used to them is it's essentially a random effect where the realizations aren't independent necessarily, but they're dependent on their neighbors. So you're just adding that proximity component of surveys that are closer together in time and sites that are closer together in space may be more similar to each other than sites that are farther away, which I think is quite easy to wrap your head around, that is useful and relevant. And yeah, I think at this point you can turn them off, but by default they're turned on. Just out of principle, basically, that to account for these repeated measures that we should have them in.
Yeah. Bold choice to have that by default. I love it. And so something also, another thing you have that's also very, very useful, are global local shrinkage priors for variance decomposition of the occupancy and detection linear predictors. So can you tell us what this is about? What is variance decomposition in this context? And why is shrinkage an interesting tool here?
So the intuition around it is that we have a linear predictor with a certain amount of variance, and different model components are in a way competing for that variance, or at least contribute to that variance. And you might have a bunch of predictors. You could have 2 predictors, you could have 200 predictors. And then you have random effects, and then you have species level deviations, because every species has its own response to the predictor, and species level random effects. So we potentially have a large number of variance components, and it's actually, traditionally, you would just put independent priors on all of the coefficients on the species. Well, the species coefficients might be modeled hierarchically with a shared scale, but the coefficients would probably be independent. The variance components of the random effects would be independent, and they've pretty well shown that the prior predictive distribution of these models, as you add more and more predictors and more random effects, the prior predictive distribution gets a bit silly, where you have a huge amount of variance that you are expecting a priori to be captured by your model components. And what the global locate shrinkage priors does is it kind of turns it on its head by saying, I'm going to put one prior on the overall variance of my linear predictor, and the prior distribution for that variance, I've chosen a student T, just because it has a nice thick tail that if you have a lot of variance in your linear predictor, that can easily be accommodated. The key intuition is that you now partition this global variance to your different model components via a simplex. So at this point, you have a global variance and a simplex that you're estimating from your data, and it basically neatly partitions your available, let's call it variance budget, across an arbitrary number of model components. So like I said, you could have literally hundreds of predictors in there, and it should be fine for the model because your total variance doesn't really change. It just gets partitioned between these different model components. And the simplex has an underlying parameter, or it could be multiple parameters, but in this package, it just has one. And that parameter determines the sparsity of the simplex. And the sparsity of the simplex basically determines how evenly our simplex is distributed. So when you have a sparse simplex, there's a few components, a few model components that are explaining most of the variance. So let's say you have 20 predictors in there, none of them are important except for one. You expect the simplex to be very concentrated around that single model component, which means the simplex is sparse because most of the simplex values are 0 except that one, which is very high. And if you have an even simplex, you expect a more even distribution. So this predictor has like 10%, and that predictor has 7%, and this one maybe 15% of the simplex. That's actually a hyperparameter that's included in the model as well, which basically means that there's a prior over the sparsity of the simplex, which means that a huge amount of model configurations essentially are possible using the exact same hyperpriors. So theoretically, this model should basically run whether you have one species or 100, 0 predictors or 50, random effects everywhere, or none at all. That should all just be handled by having these two priors on the overall variance and the simplex decomposition.
Okay. Yeah, I love it. This is super interesting. And so to do that, what are you using under the hood I'm guessing it's from Stan.
Yeah, so actually I'll just backtrack and give credit where it's due. This basically comes from the R2D2 literature where they decompose R squared because
Yeah.
you can get the explained variance as a deterministic transformation of your R squared. And so what they do is they set a prior on R squared, deterministically transform that to your explained variance, and then simplex decompose that. I skipped the R squared because the R squared gets a bit hard to interpret when you have count variables and also logistic. So the occupancy side remains a Bernoulli, so a 1 or a 0, and the detection rate is a count, so it's Poisson or negative binomial. R squared doesn't work as nicely intuitively as it does for nice Gaussian models. So I skip the R2 stuff. I go straight to the variance prior. And under the hood, I just produce a simplex of arbitrary length. And I have to give thanks to the Stan developers because they have recently put in functions that lets you simplex transform just a free vector with one less element than your desired simplex, which means that under the hood in this model, it looks at all the variance components. So how many species, how many predictors, how many random effects. Based on that, you know how long your simplex has to be. The simplex is then produced under the hood. And yeah, what I use in Stan is a variance parameter with a student t prior and a simplex with either a Dirichlet or a logistic normal prior for the simplex.
Yeah. Yeah, so you're removing 1 degree of freedom because, well, you have to. Yeah. Sounds a lot like the zero-sum normal distribution that we worked on the Pine CSAP with Adrian Siebold.
It is, and there's a lot of overlap between zero-sum normal and the simplex, and both of those constraints are getting a lot of use in the package because the package accommodates, for instance, categorical predictors, and instead of setting a reference category, I just model those as zero-sum normal based on how many categories there are. But every categorical predictor can have an arbitrary number of categories. So you might have habitat type like forest or swamp or desert as a categorical predictors with 3 levels, but you could also have one with 6 or 7 levels. So based on that, it just produces a zero-sum vector of the appropriate length for every categorical predictor. So actually a lot of the stuff that's in this package now has implemented really recent additions to the Stan language. So the timing's been really good.
Yeah, I'm guessing that made your life much easier because before that was much harder to do.
Yeah, and it was just really messy. There's still that you have to have a bunch of unconstrained parameters in your parameters block and then use the transform parameters to actually constrain them. So one downside is still that your final fitted object is going to be bigger because it has a bunch of these unconstrained parameters that you need to produce the transform parameters. But I mean, that's a small price to pay because it just makes modeling these types of things so flexible.
Yeah. No, exactly. That's really been a game changer to have the zero-sum normal constraint in Pareto and in Stan. So definitely encourage people to use that more. It's great that you're using that under the hood because, again, these are complex mathematical objects in the sense that they're not very intuitive at the beginning. And so being able to just have that under the hood for the users, they don't even have to care that it's actually using that. It's just like, just use that because it's better. Like, it's going to make your model better.
Yeah.
That's the only thing you need to know. And actually, you don't even need to know about it. It's just like, that's what you need to use. Just do what the doctor said. And that's going to make your model better. So we're going fast here. And for people who want to have background on that, there are at least 3 episodes they can listen to. 74 with Adrian Zabelt, who is the father of the zero-sum normal. Episode 133 with Sean Pinckney, who is one of the people who developed zero-sum normal constraint on the Stan side. So if you guys want the background on that and all the cool thing you can do with that, definitely listen to that one. Adrian also make a guest star appearance in that one. And finally, episode 134 with David Cones, because in this one, David goes through and actually demos live the AR squared prior, which is the R2D2 prior, but for time series, for especially autoregressive time series. And it goes into a lot of the concepts that you just mentioned, Matt. So if people are interested in that, definitely check that one out too.
Just another nice thing with the zero-sum stuff is that in this model, for instance, I have species level random intercepts that sort of capture the overall detection rate of a given species in your data set. But then if you have, let's say, a categorical predictor and you model that hierarchically, you have an overall habitat effect to say this habitat has this influence on just your species and a species level offset realization of that. So there you get into actually the zero-sum matrix where it has to sum to zero over the categories, but also across your species so that your overall effect keeps that nice, that zero-sum interpretation. And it means that the intercepts in these models are actually the averages over the species over all of your categorical predictors. Whereas if you don't zero-sum anything, you get those wider uncertainty. You actually have to go and derive those means afterwards in generated quantities, and it gets really hard to keep track of. So yeah, the zero-sums have just been amazing because of, identifiability of your parameters in the strict sense. But also, sorry, I just actually blanked on what I was saying.
That's normal. These are complicated objects, as I was saying. But yeah, basically you're talking about the fact that it can get intricate because these are like Russian dolls where basically you might need zero-sum normals all the way down, because if you're dealing with categories and on top of that simplexes, then you have a bunch of sum to zero constraints that you need to avoid over parameterization in your model. And so basically what you're doing is getting the headache out for the users, which I'm sure everybody will appreciate. And actually another concept I wanted to touch on is within chain parallelization, because that's something I think a lot of listeners have heard of on the show, but never necessarily actually used because it's quite new. So in your experience, when does it actually help, and when is it not worth the complexity?
Yeah, that's a funny one. It's not really intuitive, I find. So just as background, within chain parallelization, let's say you still want to run 4 chains. Normally you just run 1 chain per core, but if you have more than 4 cores available on your computer, you can actually split the work of the individual chains across different cores. So for instance, if you had 40 cores and wanted to run 4 chains, you could run the work of each of the chains across 10 different cores. There's a lot of overhead associated with within chain parallelization, as I understand it, a lot of copies to go across the different cores. And I've actually found that it often does not speed up the model. I think normally you cut the likelihood computations over your sampling units. And ultimately, in these types of models or in occupancy models, the sampling unit is the site. So you compute all these likelihoods for all of the species at each different site. And what I have found is the more expensive the per site likelihood computation gets, the more benefit you get from it. I have not really figured it out. I end up testing it out on the different models that I have. Within chain parallelization is optimal. You can just turn it off because a lot of the time it won't speed up. Yeah, I'm also not sure what to exactly parallelize, because you could just parallelize the likelihood function and do everything else inside, for instance, the model block or transform parameters. But I've actually put all of this stuff associated with the sites inside of the parallelization function, which I think means that ends up being a lot of copying. So a lot of data structures have to get copied. There's like 30 arguments to the parallelization function. So yeah, maybe at some point I will try and figure out if there's a better way to do it. But ultimately it does come down to trial and error, really, and how many cores you have. I'm not quite sure. I think it is from what I've read on the Stan page, there is no cut and dry sort of outcome with parallelization.
Mm-hmm. Yeah, it's also my experience, but this is not really my area of expertise. I'm sure Adrian, for instance, if he were on the show, and he will be soon again on the show, by the way, maybe he'll have things to add. But another concept you're using also in your package is Monte Carlo integration to deal with high Pareto-k values when you have observation level random effects. So listeners may have seen that in their models. When they are using RVs, they may have a warning that there is a high Pareto-k value in there that makes the comparison with leave-one-out cross-validation not trustworthy. Maybe they don't even know what that means. And so this is related to that. So can you walk us through what that problem looks like in practice and how the Monte Carlo integration fix works?
Yeah, I'm actually with your hypothetical users, because I do not have a good understanding of what leave one out cross validation is actually doing, and don't have an intuition around the high Pareto-Ks. I do understand when they come up, and in an occupancy model, like I said before, the lowest level where the likelihood factorizes, which is the level where you want to compute the log likelihood for leave one out cross validation, is the site. And as I mentioned before, we have these site level random effects because, well, we have the repeated measures at this unit as well. So I feel like they should be there, but it means that when you have a random effect or a parameter associated with the level of the observation, you end up getting these high Pareto-k values. And it's something that I've been encountering or struggling with for a lot of ecological models, because, well, we tend to have random effects at the level of the site when you want to capture variation between the sites. And I got the tip from Aki Vettari. I don't know how to pronounce his last name, on the Stan discourse, and he said to use Monte Carlo integration, which is essentially in generated quantities for each for each MCMC iteration within each draw, you would do a bunch of draws, or you would compute the likelihood many times for what is essentially a posterior predictive random effect. So let's say you have 50 Monte Carlo draws. Within each MCMC draw, you compute the likelihood 50 times with a different value for that random effect, and then you average it out within each draw. And this is still fast because it's happening in generated quantities. So stuff that happens in that block is fast. So it doesn't add that much to the runtime. But I found it very much reduces the Pareto-Ks. So usually I'll get somewhere of, I don't know, 60 or 70% of my observations have high Pareto-K values without the Monte Carlo integration. And it might go down to 10%. And those probably genuinely reflect poorly fitting observations or poorly fitting sites. So it's just one, I don't know if it's the most principled way. I think it's kind of a brute force way to go about it, but I'll take anything to reduce those high Pareto-Ks and make my model comparison a bit more trustworthy. Because the key thing is when you have observation level parameters and you get those high Pareto-Ks, it's not necessarily that your model is bad. It's just that leave one out cross-validation isn't working well.
Yeah, exactly. And I mean, a lot of time, especially with count models, you will see these warnings, and that's because you have some highly influential observations. And so that means that if you remove that observation, then the landscape completely changes, because that observation is very highly influential and it determines a lot of what the model is saying about the phenomenon. But if you remove it, and if you have a very low sample size, which can happen with count data because it's discrete, if you just have, like one count of that data, as I understood, then that's a highly influential observation. And if you remove it, that means leave one out cross-validation is going to change a lot depending on which observation you remove, and that can change the results a lot, and that's not what you want, because that means the number you see is not necessarily very reliable and reproducible. That's also yeah.
Have you found this in your experience to be common with count models more so than continuous data?
Yes, but that's anecdotal evidence. Like, I'm sure Aki would be a much better interlocutor than myself to tell you the actual scientific truths about that. But my experience, since I work also a lot with count models, is that often Pareto-k is problematic for count models. I think I remember.
Is that also for a negative binomial? Because I feel like the Poisson is just like completely restrictive and unrealistic, especially for ecological data. Have you found that high Pareto-Ks tend to persist with negative binomial as well?
Honestly, that I don't know. Like, I don't remember. I didn't pay enough attention, I think. What I know is that, I almost know, and I almost never can use a pure Poisson distribution. Like, it's almost always restrictive because of the mean equals variance constraint. It's just like the likelihood is just too constrained and not variable enough, and then I have to use a gamma Poisson. Or
actually, I encountered it recently in a wild data set where the Poisson was preferred to negative binomial, and it was an incredible feeling.
Yeah. Yeah, that never happens. Yeah.
No.
Yeah.
I don't expect it will happen again.
No, yeah. Almost always. I mean, I always try the Poisson because, like, it's the scientific process, and, I have to justify why I'm using the gamma Poisson. But, like, almost always, I can't even remember a case, but that doesn't mean never happened, where I could use a Poisson. Like, it doesn't pop into my mind.
That's where I quite like I don't know if you've come across the PC, the penalized complexity priors,
Right.
where if you consider the Poisson to just be a special version of the negative binomial, you can set a prior that essentially penalizes how far it differs from a Poisson model. So you can kind of have your cake and eat it too. You can, if there's no evidence in your data to suggest that overdispersion is present, you can just fit a negative binomial model that basically looks like Poisson. But if there is evidence, then there's plenty of space in the prior for that to occur. And that's actually the default prior that's in the negative binomial overdispersion parameter. Because the R
cool.
package, the R package allows you to have overdispersed data. So you, instead of a Poisson, you fit a negative binomial. And I think it was Aki that did some work to look at which values for an inverse gamma on the overdispersion parameters most closely mimicked the PC prior on it, and that's the prior that's now default in BRMS for negative binomial models. So it's an inverse gamma 0.4, 0.3. So that's what's that's what implemented by default.
Wow, that's really cool that it's the default. Yeah, so penalized complexity priors, I love them. I use them all the time for GPs, actually, especially for amplitudes and length scales. A bit more for amplitudes, because most of the time when I'm using GPs, I'm using HSGP, and the length scale is actually fine with HSGP, because if you're using HSGP, most of the time you have a lot of data, and so you have a lot of data which can inform the length scale, and so you're fine. The amplitude is a bit more complicated, and so I always use a penalized complexity prior on the amplitude, which is awesome because it's very intuitive to define. And on the length scale, I've tried it, but it's actually harmful. It's much better to have like a more diffuse prior and then have the data move the prior on the length scale if you have a lot of it. And so, yeah, like, and then the other PC priors, we need to add them in PyMC. I know Bill Engels has been doing a lot of work on that, and he's actually being the one opening my eyes to the awesomeness of PC priors. That's thanks to him that I use them in GPs. And we have a project to add them into PyMC, but we never get to it. If anybody wants to work on that with us and actually get that across the finish line, please contact me. But yeah, we need to add that to PyMC because it's extremely helpful. And I know Bill has been working on that. He's been working on some GP stuff also, so he'll come on the show very soon. I've been working on having him on the show, so that will happen very soon. But in the meantime, and while we're working in adding PC priors to PyMC out of the box, you can already do that. But you can already listen to episode 136 with Janet van Niekerk and occARU. They work on INLA, so nested Laplace approximation. And in the episode, we talk exactly about PC priors. And so if you just want to hear about that, I think it's in the chapters. You can just jump into that. But it's a fun episode to listen to. And yeah, they already have a bunch of PC priors coded into the INLA package. That's both for R and for Python. So yeah, for people interested in that, feel free to look at that. I'm sure you'll find some very interesting nuggets of codes and concepts in there.
I think the PC priors are actually a bit orthogonal to the variance decomposition priors because the scale or the amplitude of the GPs is just one of the variance partitions that lives on this simplex. So I don't even know I don't think it would be possible to even put a PC prior on there because that variance partition is just absorbed isn't the right word there. It's just one of the components that lives on that simplex that decomposes the total variance.
Yeah, I mean, I've never had to work on that case, but I agree with your prior that yeah, it's probably mutually exclusive, and
I think so.
it's
Yeah.
a trade-off. Yeah, it's a trade-off you have to take depending on what you're mostly interested in that case.
I do enjoy, or I enjoyed seeing that when I wrote the function that lets you set the hyperparameters for your priors, that you have a potentially very complicated model with predictors on occupancy, predictors on detection, random effects, etc. But the actual list of parameters that you need to set priors on is quite short. Whereas if you didn't have these decomposition priors, you potentially have to set priors for every coefficient, for instance, or the variance of every random coefficient slope type thing. And if there's one thing that writing this package has sort of taught me, it's just the choices you have to make when you write a package that's sort of general purpose and lets you fit arbitrary number of species, arbitrary number of seasons and predictors and stuff like that. Like the sort of classical approaches of just having a regression model with maybe a couple of coefficients is really such a narrow version of what's possible with probabilistic programming. And a more complex model really forces you to think about how to set principal priors that are essentially generalizable to a huge number of model configurations.
Yeah, exactly. Definitely. It's incredible to see how models are actually incredibly customized, even though you think you're working on a classic simple model, right? And so I'm gonna start to have playing us out here, Matt, because I don't want to take your whole lunchtime. But
Sounds good.
we've been, yeah, I'm very happy because we've gone through a lot of the technical topics I wanted to touch on with you. But a question I always love to ask people who work on packages is, when does occARU break down or underperform? What kinds of data sets or questions is it not the right tool for? And what would you tell someone before they reach for it?
I think I wouldn't say there's a huge learning curve. It's a complicated model that I've tried to make as accessible as possible with just a couple of functions. There is a big part is the chosen survey interval, which is basically how do you bin your data? Do you group it by day or week or month type thing? So if you have years and years of data and your observation level is how many individuals or detections you got of each species per day, that model will be incredibly slow to fit. Whereas if you have longer, like multi-year data, you might group by a week or 2 weeks. So that's a bit of a where big data can still be accommodated by choosing that survey interval. But overall, if you have lots of data, lots of sites, this will probably end up being quite slow. And I work on a MacBook and I've got a Apple Silicon and it's not super slow or anything, but I've seen people try and use it on a not as fast a computer and it's already quite slow. I mean, these people still have, a lot of these data sets will have tens of thousands of observations even after a thinning interval. So that's ultimately still always going to be a lot of data, especially when you have these random effects. So yeah, I think the thing is, I don't know what would otherwise suffice and be a lot faster. Because even if you do collapse it down to ones and zeros, like you still end up having a lot of sites and a lot of surveys. You just have a different observation model and maybe not as many random effects. So yeah, I would say the biggest bottleneck will be really large data sets, and also potentially not reducing the resolution enough of the data. So if your model runs really slowly, you might even group it by month and just have how many counts per month did we get, and that it actually doesn't make any difference at all for getting occupancy. So if you're only interested in occupancy, you can just group. You can have huge grouping periods, and it still gets you occupancy. So, yeah, probably speed. I would have to say, given that it's Stan and potentially it can be quite complicated with many sites and slow to fit, I would say.
Mm-hmm. Yeah, that makes sense. And yeah, grouping always your friend. I had the same could have the same issue when I was working on electoral forecasting models. So I definitely understand what you're saying.
Yeah.
And actually for an ecologist or an applied researcher who've been listening to us right now and who wants to start using occARU on their own, where do you point them? And also what's next for you for the roadmap on for the package?
So you can download the package on GitHub, and the package I don't think will be on CRAN because it uses command stan R in the background, which has the latest version of stan. So for instance, all this zero sum and simplex constraining wouldn't be available on rstan, but command stan R isn't on CRAN, and there's no plans to put it on CRAN. Roadmap for the package is I'm nearly finished with the multi-season version. So that's where you start to get into like dynamic, how occupancy can change from one season to the next as a Markovian process. So that's where you get it really in the hidden Markov side of things. Once I have that down, I have a lot of work to do myself using this package because for my postdoc, I mean, my main motivation for developing it was that I didn't feel that the current methods were able to fully exploit the information that's actually present in these data. And when people want to know, like, hey, how good is our camera trap data? I can't really answer that if I have methods that only touch on a fragment of the information that's actually contained in them. So I hope to be ironing out a lot of kinks as they come up. Like, it's unbelievably easy to introduce bugs into code. I've come to discover making this R package. Yeah, I'd like to get smooth sailing and hopefully get people using it and tell them what they need, what they're looking for, and obviously bugs that they're finding. And I just like to keep improving it to expand on it and making it more customizable as well.
Yeah, sounds like a great roadmap. Very exciting, and hope you'll manage to do that in the coming month. You seem to be on a good cruising speed, so really rooting for you. And well, let's go into show, Matt. I think it's a good stopping time. We've been covering a ton of topics. I'm very happy about that. Before letting you go, of course, you listen to the show, so you know I have to ask you the last two questions. I ask every guest at the end of the show. If you had unlimited time and resources, which problem would you try to solve?
Yeah, so firstly, thanks for having me, and yeah, it was great. The problem I'd like to solve is habitat loss, and just the destruction of the natural world around us is 100% the thing that I would like to solve the most. I don't know if there is a clear solution. I'm fairly cynical or pessimistic about it, but yeah, if I had infinite time and resources, that would be what I would like to work on.
Sounds perfect. Sounds yeah, like a very, very important problem indeed. And second question, if you could have dinner with any great scientific mind, dead, alive, or fictional, who would it be?
Yeah, I had to think about this because I knew the question was coming, and I think it would have to be Geoffrey West, who's a physicist that wrote a book called Scale, which is probably my favorite book of all time and changed the way I look at the world. So I think having dinner with him would be awesome, and I actually think it's worth people listening or reading his book. It's a fascinating story.
Okay, yeah. I didn't know about him, but that sounds interesting. So thanks for educating me, Matt. And well, on that note, let's call it a show. Thank you so much again for coming in the show, Matt, everybody. There will be a lot of show notes for this one, so make sure to check them out if you want to dig deeper. And Matt, thank you again for taking the time and being on this show.
Thank you.
This has been another episode of Learning Bayesian Statistics. Be sure to rate, review, and follow the show on your favorite podcatcher, and visit learnbayesstats.com for more resources about today's topics, as well as access to more episodes to help you reach true Bayesian state of mind. That's learnbayesstats.com. Our theme music is Good Bayesian by Baba Brinkman, feat. MC Lars and Megaran. Check out his awesome work at bababrinkman.com. I'm your host, Alex Andorra. You can follow me on Twitter at Alex_Andorra, like the country. You can support the show and unlock exclusive benefits by visiting patreon.com/learnbayesstats. Thank you so much for listening and for your support. You're truly a
good Bayesian. Change your predictions after taking information in. And if you're thinking I'll be less than amazing, let's adjust those expectations. Let me show you how to be a good Bayesian. Change calculations after taking fresh data in. Those predictions that your brain is making, let's get them on a solid foundation.